Done. Okay, we're good? Okay, guys. Hello. Welcome. My name is Lindsay Hooper, and I'm actually the organizer of Time Series New York. Thank you guys all for braving the weather and coming out here. We really do appreciate it. This meetup is run by a company called Timescale. We're an open source database powered by Postgres, and I got to put it out there, we are hiring across the board. If anybody is interested in anything, feel free to talk to me after the fact, or any of my engineers who are going to wave at you right now from the back row. So we're here to hear Gary Elliott from Google Bigtable talk about time series data on Google Cloud Bigtable. From there, we're going to hear Devin Petikolos?
Yeah, that works.
Yeah, great. Close enough. Kind of deliver a short case study on what working with Google Bigtable has done for the company he works with, Odin. Last thing, we're going to take questions at the end once everybody is done speaking. So hold them to the end. I will walk around with a microphone, hand it to you. You'll say the question into the mic, and then we'll get going. So with that, I want to welcome Gary. Thanks, guys.
Hi, I'm Gary. I've been working on the Bigtable team for 3 years now. Before that, I was doing stuff in finance and used a lot of time series data there as well. All right, so we'll talk about a few things. An introduction to Bigtable, Cloud Bigtable specifically, if you haven't heard it, and why it's actually a good fit for time series data. We'll talk about schema design. Bigtable is a NoSQL database. How do you design a NoSQL schema that works well with time series data? There's actually a really nice open source ecosystem of tools that work with Cloud Bigtable to make the time series stuff a lot easier. We'll talk about those and talk about some customer experiences on Cloud Bigtable, including Odin's. So the marketing slide on Cloud Bigtable. It's a petabyte scale, fully managed NoSQL database service, low latency, random data access, etc. Bigtable was originally written inside Google for the search index. Right? So it was built to store a copy of the World Wide Web and index that and serve it up. Since then, it's used on hundreds and thousands of projects inside Google, and including some really interesting time series use cases, which we'll mention. One of the key features of Cloud Bigtable is its scalability. It's a distributed system that is basically designed to scale linearly. And you can take that out, very far along the curve. You're going to get roughly linear performance as you add nodes to your Cloud Bigtable cluster. That's a really nice property for a number of reasons. It certainly helps, say, predictable cost. If your traffic doubles, triples, et cetera, overnight, you can click a button, add nodes to your Cloud Bigtable cluster, and you can be pretty sure your capacity is going to scale linearly, which is really nice for planning purposes and everything else. So a bit about how Cloud Bigtable works under the covers. Clients, running on a VM or something on Google Cloud, hopefully, talk to a single endpoint which distributes traffic across a number of Bigtable nodes. And the Bigtable nodes are sort of what you pay for and are responsible for serving the data. And drilling one step in, the Bigtable nodes themselves actually aren't responsible for storing any data. They're responsible for serving the data and managing it, but the data itself is stored in a distributed file system called Colossus. Colossus is sort of the distributed file system at Google, and it is underneath pretty much all of the databases and structured storage systems. And this has some really nice properties because Cloud Bigtable can notice that, let's say, in this example, those files A, B, and C are all being managed by one Bigtable node. And a bunch of clients really want the data in one of those files. and that node is becoming overloaded. Bigtable can notice this and rebalance the data dynamically. And no data needs to get copied around between nodes. It's really just saying, well, now this second node here in the middle is now responsible for serving data in file C. That's a very fast operation. It can happen dynamically. In fact, that's going to happen all day, and you're not going to notice it. Bigtable is just going to transparently do that in the background to make the most efficient use of your resources as it can. Likewise, one thing you might want to do is add or remove nodes from your cluster. This can just happen sort of in response to traffic. Like, maybe you get a lot more traffic during the day and you want to add some capacity to your cluster to handle that load. Or maybe at the end of the month, you need to run some big reporting job and you want to, add 300 nodes to your cluster to handle that type of traffic. That's really easy to do with just a click of a button or an API call. And Bigtable will add those nodes and, depending on the size of your data, 10, 15 minutes later, it's done this great job of shuffling the data around. And you've just scaled in a linear fashion. And one of the things that really makes that possible is, again, this decoupling of compute and storage, right? The Bigtable nodes responsible for compute, serving the data. Colossus file system is responsible for the storage. So what does Cloud Bigtable actually look like when you go to use it? It's a wide columnar data model. You might be familiar with like HBase, right? HBase is an open source project that was started after some smart engineers read the Bigtable paper that Google published, and you might be familiar with this type of data model. Basically, it is a distributed key value store with an extra dimension. There's a time dimension for each cell as well, which we'll talk about, very relevant to time series. There's exactly one index in Cloud Bigtable, and it's the row key. So as you can see here, a row in Cloud Bigtable, say, has a key like R1. You can have one or more column families. Column families are collections of columns, just a way to group them. And within a column family, you can set a garbage collection policy to say any data in this column family, only keep around the most recent 10 versions or the last 30 days of data, something like that. So that's at the column family level. Within a column family, you can have any number of column qualifiers. So this is, remember, it's a schemaless NoSQL database. This is just more data. You set this on the fly. So you can have a column qualifier with any data in it. And this is a sparse data model. So unwritten cells don't take up any space. So one row could have 3 column qualifiers, A, B, and C. Row 2 could have 3 column qualifiers, D, E, and F. That's fine. That's perfectly fine. And then within each one of these cells, so here at R1, column family 1, column qualifier 1 in the upper left, you can have many versions of that piece of data. So that gives it this 3-dimensional data space. So basically, it's a version for every cell, but it defaults to using an actual timestamp. So the server timestamp is the default. You're welcome to set your own timestamp for every value, in case that doesn't work for you. And the garbage collection policies work off that timestamp. So saying, hey, I want to keep around the last n days of data, assumes there's a timestamp in there and it can delete data that's old and you no longer use. And that's set at the column family level. And so you see here just a visualization of a stack of cells where you can get, by default, you would just get the latest version, and you can go back in time to get previous versions as well. So that's a little bit about Cloud Bigtable, but why is it good for time series? It's a general purpose database used for things ranging from Gmail to search indexing to Google Maps, but why is it good for time series? Well, so one nice thing is it's fully managed, right? That's just a generally good thing about some of these cloud services. You don't need to manage something yourself. It will handle pretty much any practical volume of data. A lot of time series use cases call for ingesting an awful lot of data and probably keeping it around for a long time, and Bigtable makes that very possible. It scales up or down with a single click. And that's great for maybe your backfilling data or your traffic spikes or something like that. Bigtable handles that very gracefully. It allows fast access to sequential data. And this is really important when you go to use Bigtable for time series use case. If you lay your data out so that it is sequential within the row space, we'll talk about that later, you get very fast access to that data. It scans forward through the row space very quickly. As we saw, time is a first-class citizen. Each value actually has an associated timestamp, and you can make use of that very effectively for time series schemas. There is this TTL-based garbage collection policy, and a lot of times use cases, you may not find value in data more than, say, 6 months old or something like that, and that type of garbage collection is built in. Cloud Bigtable supports regional replication. It's eventually consistent replication between Bigtable clusters, and that lets you do a lot of things, including separate out like read and write workloads. If you have ingesting data into one cluster and you want to run analytical queries or something in another, you can replicate between those two clusters seamlessly and split your workload like that. And as we'll see later, open source actually fills in some of the domain-specific gaps that Bigtable has because it is a more general purpose system. There's some great open source tools that will help you work with time series data more effectively. Okay, so schema design. This is one of the hard and interesting parts of working with Bigtable. It's a lot different from working with Postgres or SQL Server or something where you have schemas and SQL and all this stuff. So here's some basics about working with rows and schemas in Bigtable. Updates are atomic, but only at the row level. So there's no cross-row transactions, things like that. Those are all sort of thrown away in favor of this sort of like huge scalability. So if you have one entity and happens to live in the same row in Bigtable, meaning that has that single row key for all the values, you can update any number of columns there atomically. So that's a nice feature. You will generally want to store items related to a single entity in a single row. One of the reasons is because of that ability for atomic updates. But when you don't need atomic updates and you have a particularly large entity, we kind of say maybe more than 100 megabytes, something like that, split it up into multiple rows. That's fine. That's not going to cost you anything. Rows are sorted lexicographically by the row key. So R1, R2, R3, etc. And this is something to keep in mind because when you are sort of scanning over your data, you want to make sure that the data is laid out lexicographically so that you can scan in one big scan, contiguous data, not skipping over anything. And that's going to be a really efficient way to use Bigtable. And what that means is you should try to store related entities in adjacent rows. So if you always want to get, say, R1 and R2 together, make sure they're laid out together so one particular Bigtable scan operation can pick them both up together. So you might be getting the sense that this row key in Bigtable is really important. So figuring out, and you only have one of them. Remember, there's no secondary indexes, nothing like that. So the row key is very important. So you want to figure out a key strategy for you that facilitates your most common queries. If you do something all the time and then maybe on some administration page you run a different kind of query, optimize for the thing that you care about the most because, again, you only get this one row key. It's very important to choose a row key that helps distribute the reads and writes across the key space to avoid hotspots. And I'll show you an example of some things that do a bad job of avoiding hotspots and a good job. Hotspots is when all the requests are going to one or two of those nodes instead of spreading out across the 10 or 50 or 100 that you might have. So one thing you want to do is avoid monotonically increasing keys. So relevant to time series data, don't have a key that is just a timestamp and then a bunch of columns for all the values that happen at that timestamp. You don't want to do that because that timestamp, that's just like one tiny little range, and the next couple timestamps after that are likely to all live on one server. And so if you have all the data coming in for right now, 1 or 2 or 3 timestamps, they're all going to slam onto one server and then move to the next as time passes. And that does not work great. It takes Bigtable a while to respond to that type of thing, and you'll want to avoid that in your row key design. A combined key strategy is, packing multiple pieces of information into your row key is usually a good way to sort of make effective use of it. So one of the techniques you can use is when designing a row key for Bigtable, especially for these time series use cases, is called field promotion. So the top row here, you are collecting some metric from a system, right? And the row key you chose in this first example is maybe the name of the metric, mem usage. And then you have columns that have all the data for that. So a timestamp, maybe you have a bunch of timestamps there, the user associated with that metric, and the usage level, something else. That's problematic because if maybe all of your devices, maybe there's a million devices out there that you're monitoring that all have a mem usage stat reporting back every 10 seconds, all of those devices are going to report back and write data exactly one row, which is owned by exactly one server, and you're going to slam it. That would be what we call a hotspot. So how can you avoid that? So field promotion is the idea of taking one of these columns and putting it in the row key. So in this example, what if you put the name of the metric and then append the timestamp after that? That is really potentially good. It might be better. But again, all of the, usually data is coming in for right now, right? So it's not that much better because as you sequentially write data as time increases, your row key here is just, again, monotonically increasing, right? The timestamp is just going to go up a little every time, and a bunch of writes are going to still focus on that one Bigtable node that handles that, and you're going to hotspot on that node yet again. So we have another field that we can potentially promote to the row key to make this better. The user field actually might help here, right? Because maybe there's a lot of users and this lets you construct a key that lets Bigtable write things that are not contiguous, right? So they'll have things coming in for mem usage for user A, user B, user 1, 2, 3, etc., and for a timestamp. And it's going to spread things out a little bit more across the key space. You're going to avoid this just contiguous, like a laser beam writing into one spot. So field promotion can help out with this. And this is great for avoiding hotspots, but you might have to rework your queries, right? Like your queries to Bigtable are now going to have to be aware of this new row key structure. If you want to query across multiple users, you're going to have to get more than one row, things like that. So it's a trade-off of how you can design this key. It's a bit of an art more than a science. Another thing you can do, another technique is called salting. This basically, kind of like sharding, right? Like it adds an additional calculated element to the row key that forces the writes to be non-contiguous. So for example, if you had a timestamp in the row key, you could take the hash of that timestamp and mod that with, say, the number of nodes in the cluster. You have a 10-node cluster, you're going to get some integer, and put that in the row key. And then what you're doing is splitting all the writes to some number of basically shards that are sort of distributed throughout the key space, which is really good for avoiding hotspotting, because now instead of laser beaming on one node, you're spreading this out to maybe 10 or 20 or 50, whatever you decide. So that's really good for avoiding hotspots. And this is simple to do. It's a very simple function you can run on your row key. That's pretty cool. But now all your queries have to read all of the salt values, because each individual value is going to go to one of these buckets. You don't know which one necessarily, maybe many at the same time. So your queries suddenly get a lot more complicated. You're doing a bunch of things in parallel maybe to read all the salt buckets and then join them up in your app together. So that's a disadvantage to this. Also, it can be hard to find a salting strategy that scales up and down with the size of your cluster, because with Cloud Bigtable, we encourage you to decrease the size of your cluster when traffic is low and increase it as high as you want when traffic is high. And your salting strategy is probably really different if you have a 3-node cluster or a 100-node cluster, right? Like how many sort of salt buckets do you want? How many shards do you want would change. So it kind of has to be static. It can't, you'd have to rewrite your data if you wanted to change the number of buckets. So that's another challenge with using this technique. We have this really great tool called Key Visualizer, and it can help you sort through all these tricky issues when you're designing your row key. It's kind of hard to tell from this image, but back to present mode. It basically visualizes traffic to your Bigtable across the row space. So on the left, it can't really see, but it kind of like parses out pieces of your row key for you and shows you where, and then on the x-axis, it's time, and you can kind of see which part of your row space gets the most traffic over time. And something that's really bright, like there's a really bright line right in the middle, that shows you that that row or that row space is getting tons of traffic. And you can drill in and say, well, how many QPS is it getting? What row keys are getting this traffic? And a bright line like that is probably a hotspot and probably associated with one of your Bigtable nodes getting overloaded, which might mean higher latency and things like that, or maybe some errors. So this tool can really help you iterate on a row key design that effectively spreads the data across your cluster and allows you to run queries quickly for the queries you care about. So that's an awesome tool. So this stuff is hard, right? Like it's hard for people who've been working with Bigtable for 10 years inside Google, and it's hard for everyone. And one thing that helps out a lot, specifically in the time series space, is some open source systems that can use Cloud Bigtable as their storage backend and give you a lot of nice time series functionality on top. So I'll talk about a few of them. And even if you don't use them out of the box, they can provide some really good lessons on how to build systems on top of Bigtable. So one is called OpenTSDB. And it is a time series database. I think it might have originally been written at StumbleUpon, an old Web 2.0 company. And originally it was written against HBase as the backend store. Again, HBase is this open source system that's kind of a Bigtable clone based on reading the paper. And HBase has a lot of similar properties. Most of the stuff I'm saying here applies to HBase as well. So the people who wrote this found themselves with a really, really scalable time series database because it was using HBase, which is part of the Hadoop stack, as the storage backend. That's really cool. And now, because Cloud Bigtable is actually compatible with the client library that most people use for HBase, you can use OpenTSDB not just with HBase as the backend, but Cloud Bigtable. And OpenTSDB is kind of notable because it was the first open source system that I know of, at least, to use this data model that's pretty popular these days, where you have a metric and some tags, like metadata associated with that metric. And the combination of tags and metrics would sort of like, make a unique time series, and you can slice and dice the data by querying for specific tags. That's kind of a common data model these days with OpenTSDB and Prometheus and Influx and systems like that. That was originally inspired by an internal monitoring system at Google called Borgmon. And Borgmon, resembles OpenTSDB a little bit, resembles Prometheus a lot. And that system uses this sort of data model. OpenTSDB exposed that to the outside world. So a great feature of OpenTSDB is that it's horizontally scalable via HBase or Bigtable. And it supports sort of a lot of the standard integrations with the sort of stack people might want to use, like Grafana, CollectD, StatsD. It can operate as Prometheus long-term storage. It will mirror your writes to OpenTSDB out of the box, things like that. So how does OpenTSDB use Bigtable? It has this, how does it make use of that data model we just talked about to build a, high-performance, scalable time series database? Their row key looks like this. So they optionally use salting. So that is an option you can set in the config. You can say, I want to have 10 salt buckets, something like that. And it will stick that as a prefix. It then resolves your metric name and all of your tags and values to like an integer and encodes it as 3 bytes. And it makes this row key that looks like the metric, then the timestamp, and then all your tag value pairs laid out like that. So that's the row key. The timestamp is the beginning of like an hour. So each row in OpenTSDB is for a particular time series, and they put an hour's worth of data there. And each column, it encodes like a data type, whether it's an int or a float. You can kind of mix and match, which is fun, inside one time series. And then they will have an offset encoded in that column as well, which is an offset against the base timestamp that's in the row key. So effectively, this stores all the data for a metric together contiguously. And the way they read data is by constructing a regular expression based on the tag value filters that you give it. And they do a big scan. So you can scan HBase or Bigtable. You can say, for rows that look like this, provide a regular expression. I want the data. And this works pretty well, especially when you want a lot of the data that's stored contiguously. Because it's going to do one big scan, and if it's not a very selective scan and wants to pull it all back, like if you want all the time series for a particular metric, this works pretty well. Just scanning is fast in these systems, and it'll return it, and it's pretty fast. It gets worse the more selective your queries get. So if you're picking out one or two, you have a couple tag value filters, and you're only picking out one or two time series, it's basically going to scan a lot more data than is necessary. So OpenTSDB is a good system. A lot of people use it in production. We have production, companies running their business using OpenTSDB on top of Cloud Bigtable. So, it's some pros here. It's horizontally scalable. So you can pretty much scale this to pretty much arbitrary amounts of data and, ingest rates and all that. There's a, standard sort of common data model that it supports. A bunch of integrations, Grafana, et cetera, come out of the box with OpenTSDB. Not very selective queries work really well. And the only bit of software you have to run, especially if you use Cloud Bigtable here, is this TSD, the actual sort of like query server. And that's a stateless thing you can run in a Kubernetes cluster or just run a couple on VMs, and it's not that hard to manage. Some cons, if you're not using Bigtable, you have to run HBase Hadoop cluster. This is not great. It has a very simplistic query language. It sort of covers a lot of what you need to do, but it is not a slick, sort of query language interface like you're going to get with PromQL or what Influx is doing and things like that. And like I said, you can end up scanning dramatically more data than necessary, depending on how selective your query is. It also, there's compression built into HBase and everything. You can probably get better compression with custom time series storage engines that can take advantage of particular aspects of time series data. So you might be able to squeeze more data into a different type of system. So another system in the open source world is Heroic. We're going to hear a bit more about this later from Odin. Heroic is a time series database written by Spotify for their internal monitoring system. So all the metrics collected by all your Spotify listens and clicks in the app go into Heroic. And it's essentially the same data model as OpenTSDB, I think. A metric and tags and values, maybe different terminology. It supports Cassandra and Cloud Bigtable out of the box as backends. And Cloud Bigtable uses the native Cloud Bigtable gRPC APIs. It doesn't go through the HBase layer that other things do. It stores metadata about the time series in Elasticsearch. So when you write data to Heroic, it indexes all those tags and values in Elasticsearch. And then it stores all the data for a particular time series together in one or more rows contiguously, which is a little bit different than the way OpenTSDB does things. One nice feature of Heroic is that it has first-class support for consuming data from Kafka, which can be useful for lots of people's pipelines. So the architecture of this system, I think, looks a little bit something like this. Data comes in, so for Spotify's case, it's monitoring data, but it could be IoT data or anything else. To one or more consumers, this is something reading from a Kafka queue or whatever. It's going to write the metadata to Elastic to index it there. It's going to write the actual data points to Bigtable. User requests for a dashboard, pretty common. Spotify has a lot of dashboards monitoring their systems. Requests from that come into these API nodes, which send the request to data nodes, which actually talk to the data stores. So they look at your filter. They're going to construct an Elasticsearch query, get back a bunch of time series IDs, send those IDs to Bigtable, and pull back all that data and do all your time series analytics and downsampling, grouping, et cetera, in the data nodes and return that back to the user. So that's heroic. That's another interesting system. This is a kind of cool one, Cortex. Cortex is an open source system that builds itself as a horizontally scalable multi-tenant Prometheus. So if you're not familiar with Prometheus, it is an open source monitoring system. It's very popular. It's tied pretty tightly to Kubernetes as the monitoring system of choice. And one decision that Prometheus made is that it's a monitoring system. It should be the last system standing if there's an outage, so it's as simple as possible. And one thing about being simple is that it's not a distributed system. It stores data in one node, and you're constrained by that. So people with larger footprints or someone who wants like an HA setup with Prometheus, you kind of have to roll your own or use one of these things that are out there. Cortex is one solution to sort of a multi-tenant or scalable Prometheus. And it, like some of these other systems we've talked about, can store data in Cloud Bigtable, it can store data in DynamoDB or Cassandra. And it's meant to fill some of the gaps in sort of the standard Prometheus that has those limitations. So it's horizontally scalable via these NoSQL backends. It has a distributed hash table-based ingestion tier, the stateless query tier. So it's designed to be a scalable system, and there's multiple companies running it as a SaaS product, like a SaaS monitoring system out of the box. It's meant to be multi-tenant, either multiple customers or just multiple teams within a company. And it can be long-term storage for Prometheus as well. I think that's how it works. And so I think the way this works with Cloud Bigtable is that it stores an index in Cloud Bigtable as well as the actual chunks. So Prometheus has this, compressed data format for time series data, and it ships that off to Cloud Bigtable and reads it out of there. That's another interesting system. So customer experiences. So I'll talk about one customer and just a little bit about what they do, and then we'll hear from Odin, who has some really interesting experiences as well. So one interesting company that we work with is called Cognite, and they use Bigtable for processing and querying time series data. They work with sort of industrial IoT type of data, and they evaluated the open source systems that are out there. Sorry. My laptop's working. Oh, one red? No, it's green. The blinking seems bad.
Huge. Good.
Huge.
Even bigger is good.
That's as huge as it gets, I think. Okay. There we go. So Cognite evaluated some of these. Does it like the next slide? Wow, I want to go back to that slide. Is it going to work? Is it going to fail again? Anyway, we'll stay here. So Cognite evaluated some of those open source systems like OpenTSDB, and it didn't work for them. And so they built a time series system on top of Cloud Bigtable. And so they have a row key that kind of looks familiar a little bit based on what we talked about earlier. They have a number of sensors on, say, an oil rig. And their row key is like the name of the sensor and then a timestamp. So this looks like, sort of like, again, hourly data stored within each row. And I think they said they store up to like 1,000 data points within each row for a sensor. So first they're grouping by the sensor ID and then chronologically. And they're storing a bunch of values here. And they're, as a reminder, you can look up directly. Like if you know the row key, you can go there directly and read all the data in the row. But again, you can scan through the row space, and that's very fast in Bigtable. So they leverage the timestamp of a Bigtable cell, and they save some space this way. So instead of putting the timestamp for each individual data point, like in the column or something, there's already a timestamp there. They leverage that directly. So what they end up with is in one of these rows for a particular sensor in a particular hour, they have one column, which is like the name of some name that means something to them about that sensor, and then a bunch of versions, each one with a timestamp that represents the timestamp for that sensor reading, basically. And they found this a very efficient way to store data in Bigtable, versus putting the actual timestamp like in the column qualifier, which is what OpenTSDB does, as a different example. And so then they're going to have multiple values here within each column in each row, and they're going to scan through. They do a lot of pre-aggregation, so they will have their own data pipeline that aggregates things and puts them in different resolutions, so they're not only sort of downsampling and grouping at runtime. They have a pipeline that stores a bunch of different resolutions of data in Bigtable, and they build a very responsive UI using that. And next, we'll hear from Odin.
Hey, how's it going? My name's Devin. I'm from Odin Technologies. Before we start, I want everyone to appreciate this slide, because in preparation for this talk, I spent a lot of time figuring out how to make a custom theme for Google Slides that uses on-brand colors. So I want to make sure everyone appreciates that. And yeah, so I'm going to talk about Odin's use of Bigtable. So as I said, my name's Devin. I'm a data engineer at Odin. I've been building analytics products now for about 6 years. Before Odin, I was working at a similar company that was doing analytics in a very different space. And I will say that I've never actually used a time series database. I have written time series data to 6 or 7 databases in my life and read from it and felt all of the pain. So to talk a little bit about Odin, so what we do is we do manufacturing analytics. So you can kind of think of us as a New Relic or, Datadog for, a manufacturer, someone who's making cable, someone who's doing plastic extrusion, someone who's doing, injection molding, which is a really funny thing because, as engineers, we've gotten really good at building tools for ourselves. We, build an API, and then we build a whole system to monitor that API and know what the performance is. And manufacturers just don't have that, even though they kind of pioneered a lot of the approach of using statistics and measurement to make things. They're still doing a lot of it with clipboards and stopwatches. So what we can come in is we can read all of their data and centralize it and deliver them a really cool product and help them make better stuff. An example of our product, so we do a lot of interactive time series data. So this is probably the main thing I'm going to talk about here. It's stuff where, I'm pulling out a large window from, the beginning of the shift to the end of the shift, and I'm trying to understand what the melt temperature of some plastic was throughout that entire shift, and was that different versus a different shift. I might be pulling out specific metrics that are indicative of the quality of the product that's being produced. We work with cable manufacturers, and when you're in cable manufacturing, the diameter of your cable, if it's too thin, someone gets electrocuted. If it's too thick, it lights on fire. So you really care about it being in this really specific range, and being able to calculate, kind of big aggregates to say, statistically, we believe this is not going to kill anyone, is really important for manufacturers. We do a lot of real-time data. So we have an iPad that's on the line that people are interacting with. We have we have these displays of live updating data of these metrics second by second. This is like totally new for a lot of these people. So it's a pretty cool, nifty feature to them. And we do a lot of like, alerting and reporting. So you might get an alert that something's going out of bounds, get an email or something, maybe a text. You get, an email that says at the end of the day, this is what the products you made, and these were the key metrics you care about those products. And answers these really big questions that are just like, am I making products better today than I was last month? Our hardware is we actually go into the factories and we install our own hardware. We use embedded Linux devices. On those devices, we're running, Python and Go Docker containers that are talking to generally PLCs. PLC stands for Programmable Logic Controller. It was invented by Dick Morley in like the 60s during a hangover. It's the simplest form of a computer that can run, a manufacturing environment. And we kind of talk to those, we read data off, and we ship it up to, to largely GCP. And a lot of this connection is happening over, wired or Wi-Fi and sometimes even cellular connections. And we're data. So right off the bat, we are, on the Google bandwagon. This is my very googly slide showing our very googly architecture. We kind of have this layer of constrained devices. So these are things like, the individual sensors or the PLCs that we're reading from. We then have our own hardware sitting between those sensors and, and the cloud. And that's what we're doing. We're running the very basic, analytic stuff out there. We have a for loop that's running that's asking what's the current state of things and then shipping it. And we ingest over Cloud IoT, which is Google's solution for getting this data from, IoT devices, and then pushing it into PubSub, which is their managed version of, MQTT, essentially. And we use Cloud Dataflow, which is actually their runner for Apache Beam for doing stream processing. I don't know if any of you guys do stream processing. If you're not doing it in Apache Beam, you're probably doing it wrong. It took me years of doing it wrong before I realized this. And then from there, we kind of fork out into two different directions. On one end, we store it, we kind of have like our hot data, our like, productized data, and then we kind of have more of our analytics data. The analytics stuff we're doing in BigQuery. So we're doing continuous writes to BigQuery using their streaming buffers to write in. And that's stuff that, I can scan BigQuery for an enormous amount of data over an enormous period of time, and I could do some crazy joins, and it's just blazingly fast because BigQuery is unreasonably good at doing that stuff. BigQuery is, Google's managed warehouse, data warehouse solution, and it's a columnar store, and it's very cool for certain things. It's not something you build a product off of because it's made for, a 20-second response time being fast. So it's more of one of those databases where you run a query and it comes back in an hour and you're like, wow, that's really amazing. On the other end, the stuff that's relevant to this talk is we're writing to Bigtable. So we are doing that so we're actually running Heroic, and we're using Heroic's consumer to write into Bigtable and ultimately serve that time series data. We're also writing to Postgres, managed by Cloud SQL. And then at the application of the presentation layer, we do a lot of interaction between, BigQuery using Cloud Composer, which is managed Airflow, which is just a cron system. It's for managing kind of jobs. We do some Cloud ML stuff. And then we kind of have our application and presentation layer, which is a bunch of services running in Kubernetes, and Heroic, which is actually translating Bigtable's time series data into a layer that our other services understand and can work with. So this is the really pretty slide. The reality is really gross. So in reality, data comes in over PubSub, and we do this thing where we write back and forth between PubSub and Dataflow. There's definitely situations where we write back to the same topics, and I have these deep nightmares that there are messages that are just going in loops for all time. Then all of that goes to this legacy Go service we have, and then that gets shipped into an instance of Kafka we are running just for the use of the Heroic consumer that writes into into Bigtable. We have the heroic Kafka consumer running. We have this needlessly large Elasticsearch cluster because we actually have the amount of space that Elasticsearch ultimately is used with heroic to store what the individual keys associated with the time series values are. We have a surprisingly small number of those. I mean, I wouldn't say it's like super small, but it doesn't require a full Elasticsearch cluster. And everything ends up in a Bigtable. That's where the vast majority of the data is. And then all of it's read through our heroic API nodes, which are also the data nodes. And then there's a Go service on top of that that translates heroic's API into something that we like more because we really don't like heroic's API. Heroic is a really interesting product for it. There's certain things about it that we really like, and then there's certain things that we definitely have our issues with. One thing I always find really funny about heroic is, so I've worked in time series analytics products for 6 years. That means all of my friends also work in time series analytics products. All my family does. It's just everywhere. And I have a bunch of people who I know work on time series analytics products at Spotify, and they have never heard of heroic, which I find insane. I'm pretty sure it's used specifically for ops there, which is interesting because I think they're using it in a use case where they're trying to understand their own systems. We're actually productizing it. So we're actually saying we're trying to understand someone else's systems and trying to deliver that as a product. One thing I do want to talk about that we've figured out how to do pretty well with heroic is trying to optimize the actual reads themselves such that we're not always reading every single metric of data. So a lot of what we're talking about here when we're talking to our customers is we're trying to tell them, okay, what was the average speed that your line was operating at? So you have this line that's producing cable and it's spinning at a certain speed. What was that average, or what was the standard deviation, or what was, any one of these aggregated metrics over, hours or days or sometimes even months? And being able to understand that from line to line, right? They might have 4 lines in a factory all making the same product or similar products. They just want to know on average which one goes fastest. So for that to pull out every single second by second metric is actually not cheap. So we have this additional layer, this additional roll-up behavior we do. So the roll-up behavior is essentially, this is what we are accomplishing with this data flow work here, the stream processing stuff, is we read the metrics as they're coming in and then roll them into batches of, this makes it look like 2 seconds and 4 seconds. It's actually batches currently of 1 minute and 10 minutes, and it's configurable to keep increasing that as our performance requires it. And the advantage there is that if we roll it up, we can hopefully select a combination of them and have like an optimized aggregate. So the way that works is, say I'm trying to calculate the average of some metric over some period of time. So what I do is I have these big rollups. So I'll select, for example, I'm trying to select this period right here. So from time 6 to time 17. And what I'll do is I'll actually select these biggest chunks from time 8 to time 12 and time 12 to time 16. And then I'll select time 6 to time 8. And then just the raw metric at the very end from time 16. And combine all of those at the API layer to create my new aggregate. What we're actually storing in those rollups, that does actually create this interesting constraint about what are you aggregating. You can't just say, it's not like the rollup is going to contain every single raw metric. That wouldn't be an optimization. So instead what we do is, say you're trying to calculate an average. Well, an average you can calculate if you store all of the count of the metrics and all of the sum of the metrics. So I had, a bunch of metrics at all these different points. Maybe they come every second. Sometimes they're missed, though. I can count the frequency, and then I can also I can sum up the actual values. And then I can add all the sums together, and I can add all the counts together, and I can divide the sums by the counts, and then I have an average for that entire period, regardless of what the size of the individual aggregates were, or the individual rollups were that created that. So this works pretty well for summing, if you're trying to come up with a large sum. It works pretty well for count. It works really well for max and min. If you're just trying to say what the upper and the lower bounds of these periods were. You can argue that there's a way you can phrase this, and you could say it's an associative aggregate, which there's a nice formal definition for. But what it essentially means is that you can keep adding these out. And probably the coolest thing about this is you can actually calculate standard deviation by this way. That's what that crazy chicken scratch is at the bottom of the slide. I always thought you had to calculate standard deviation by getting every single data point and doing the standard calculation for standard deviation. It turns out that you can do this in a live moving window associative aggregate way with these individual rollups, which is really cool. It's probably the best kept secret in data engineering right now. It kind of blew my mind when I figured it out. So yeah, so that's how we've been using Bigtable pretty heavily via Heroic. And to talk a little bit about what our future is. So Bigtable for us has been low maintenance, low cost, resilient way of storing time series data. I think in the long term, it could be a way of storing kind of any series data. There's a problem that we're trying to fix right now, which is, if we go back to this slide, is that we fork between writing to BigQuery and writing to Bigtable. And that creates ultimately inconsistencies between those two data stores. And I'd like to resolve those. So we're probably going to try and start thinking about how do we move, what could be a source of truth that sits upstream of both of those, such that what we have in our Heroic Bigtable time series data and what we have in BigQuery are just reflections of that single source of truth of everything we've ever read. There's a good chance that will be Bigtable because we've had a really positive experience with it so far. Yeah, keeping BigQuery with Bigtable in sync is pretty hard. Yeah, one of the big inconsistencies here is that Bigtable with Heroic or OpenTSDB is going to dedupe data rights for you. Something like BigQuery is not. You can, in theory, read Bigtable into BigQuery via external tables. I've done it. It's crazy. It looks really weird. I don't know how to interpret it. I wouldn't recommend it unless you're very clever. And we really need to solve window joins. So this is essentially, we know that from some period of time on some particular manufacturing line in a factory, they were producing some product. And our customers now want to know things like, sort all of my products that I've made this month by their average quality metric, or the variance in their quality metric. And that kind of stuff gets really tricky because what you're doing is you basically want Postgres for that. So we kind of accomplish this in BigQuery right now because BigQuery is SQL. It gives you a Postgres SQL to interface with. But we would like to do this live. We'd like to give them ways to do this in a faster way that lets them kind of express more complex queries. And there's more and more product demand for it, and we can't really do it necessarily in memory. So figuring that out is a big question for us. I think Bigtable is going to be part of the solution, but I don't know what the long-term solution there is. But yeah, overall, I don't think we're seeing it leaving our stack anytime soon. It's been pretty positive. We might replace Heroic in the future. If I could go back to, what was it, like 2016, we might go with OpenTSDB. But so far it works, so can't complain that much. And I think most of that is speaking to the resilience of Bigtable. Thank you. And just a heads up, we are hiring. So odin.io/jobs, especially if you like working on these kinds of systems or like working with hardware. We are also hiring for those roles. Cool.
How do you correct the issue?
Oh, please.
Should we come up for questions?
Yeah, come on up, guys. How we doing? Yep.
Yeah. Oh, true. Yeah.
Okay, I have a question. You mentioned that you store aggregated data at the time that you store the data, right?
Yes.
If you recognize in the last 48 hours, one of your sentences were sending incorrect data, that you need to eliminate this, exclude that inputs from your aggregations. How hard, how quick going back and updating all those aggregations for the last 48 hours? Is it even possible?
Great question. This is why you need to have a single source of truth where you don't do where you just store everything as an event store, and then you recompute the world when you realize something went wrong. The reality is it's in some places easy, some places hard. We run into a bigger version of this, which is sometimes we realize that a machine has been incorrectly configured for a month, and we need to replay a bunch of data into that and calculate a bunch of things. In those cases, a lot of these aggregates that are computed, that are like pre-computed before the user sees them, we're doing with Cloud Composer, which is Airflow. Airflow makes it really easy to rerun things. So as long as you're making all of your jobs idempotent, then you can just rerun a job and it'll recompute the same aggregates. And it can be very clear, okay, just rerun all of Tuesday. It's fine. We'll deal with it. In the long term, a lot of what we do is we actually store, we try not to delete data or delete rows. So we'll store like change versions of things. So this isn't true for the metrics. For the metrics, we overwrite them. But for things like I went from running this product to running this product, we let that be configurable in this way where we have we can insert a new version of it, and you'll actually just look at the created at timestamp and say this was created later than this version, and therefore this is the one I have to correct these things that were computed between the old version and the new version.
Okay. Thank you.
Further questions?
There's one over there.
Oh yeah. Hold on.
Sorry. So you mentioned that if it was 2016, you would have chosen OpenTSDB over Heroic. Have you actually done a comparison between the two, like done benchmarking right now between the two?
I did not. There was another engineer who did and felt that Heroic was a better choice. Also the same engineer who came up with the original associative aggregate kind of solution for a lot of this stuff. So, I mean, they definitely thought about this problem pretty hard. And I think, yeah, benchmarking, I'm not really sure. There was the row key thing, I think, would be a pretty substantial difference, probably for us because we have a pretty small number of metrics overall, relatively. So in case unless we had more, you would run into hotspots more with OpenTSDB. We did notice there were just the actual query language of OpenTSDB is missing certain things we were looking for as well. You can't chain aggregations in OpenTSDB. There's some cool ways you could do chaining aggregations in Heroic that solve specific product use cases we were looking for. I think the advantage of OpenTSDB, though, is that you can put Grafana in front of it and then get static images of, of time series data and include them in your email reports, so you don't have to make a backend D3 service. Like, there's a bunch of really cool things that are just plug and play with OpenTSDB, and I think that's why I like it more so than I like the API more in one or the other.
Thanks. My particular area of expertise is in response to large-scale power grid incidents. How connected is this to the concept, and of course we're dealing with time series data as well when you're dealing with a response to a large-scale power grid incident. How can you connect this to geospatial data?
To geospatial data? Oh, interesting. We have not explored geospatial data. I can say that. I don't think it would be, I think it would just be another layer on top of it, though. Not yet, yes. It would be another layer on top of it. It's interesting bringing up power failure, though, because one of the things we do think about constantly is massive, like, ISP outages, for example. Because that's a situation where suddenly there are manufacturers who would depend on you as a product to always be working for them to make their business run. You need to keep running even when that happens. So we're actually, one of the nice advantages of Bigtable is that since it's compatible with it tends to be compatible with things like, HBase. In theory, we could run HBase within, like, on-premise, for example. In theory. Not saying we currently are, but there's this argument of a lot of Google's infrastructure you can duplicate down onto an edge because it's all open source APIs anyway, and have some sort of resiliency there.
Yep, coming over.
Okay, so you could also do basically part of your row key structure be a metric, and you could do like a z-index type of thing in front of it with a timestamp. And there's one company I think called Mesa, which actually GeoMesa, which actually built something like that on Bigtable too. And there's some demos out there of how you can do it. There's a really good chapter on this in HBase in Action that goes into geospatial data using this type of row schema. It's really just about, that one's I think is geographical data, but you could combine these two approaches together and make a geotemporal database out of it as well. Sure.
Awesome. There you go.
Hi. So I'm curious, with Cloud Bigtable, how I've also heard of something called Firestore, even though I've never used it, but it seems like it's for most intents and purposes it's very similar. It's very similar or loosely similar to Bigtable. What's the differentiation there? What's
Sure.
going on there?
So Firestore is another cloud database from Google. It's a document database. So it's the document style API. That's one big difference. Another big difference is sort of the billing model. You pay per request there. And for very large use cases, that can get very expensive. For very small use cases, there's a really great on-ramp to using it. Bigtable, you kind of reserve some resources and pay for those resources. But the reservation can change at any time, but it's a very different billing model. And Firestore, I think at this point is mostly used by mobile application developers and things like that. But there's some similar underlying technologies and other things involved.
Questions? I think we have time for like 2 more, if they're out there. Sure. Hold on for the mic.
Just curious about the MongoDB and the other products out there. So if you want to actually make the selection, how would you kind of if you're trying to figure out how to differentiate the products, and so how would you? What's your guideline? It's just kind of a general kind of idea to get into this space.
Yeah, there's a lot of comparisons probably right now out there. You can find about comparisons between storing time series data in Mongo versus Cassandra versus Influx, Prometheus, OpenTSDB, et cetera. You can start by looking at that maybe from like a benchmarking perspective. A lot of it as well as sort of like the operational capabilities of the various systems, right? And the scalability characteristics. And do you want a managed service like a Cloud Bigtable, or are you comfortable running something yourself? I'm not a Mongo expert. I don't know.
I have written times. I can actually come up with this. I have done time series data in Mongo for too long. I personally would not recommend it. You can make it work. You run into, I think, a lot of the operational headaches of, this has also changed ever since they changed out the core engine, but I think there are a lot of our operational headaches to Mongo with respect to time series data because you end up with fairly large documents and things like documents changing size. You end up having to do things like pre-allocate the size of your document as soon as it gets created. And it's also just replicating those documents tends to get a little weird. And I think the main thing, like one of the first things to look at is what are the features you're looking for. So one thing we're still trying to solve are window joins. And there aren't many time series databases out there that solve that. Another thing that you might be thinking about is how much infrastructure do I want to manage? Because the nice thing about Bigtable is ultimately that it's managed and it's always there. And the regional replication is really nice too, because that saves us some additional headaches we'd be going through to make sure that we would survive a regional failure.
Cool. Anything else? Okay. Well, thank you guys. This was lovely.
Thanks.
Thank you.
We have the space for, I think, another half hours or so. Eat, drink, be merry, finish the food, finish the beer, finish the